Okay. Today we will begin circuit analysis of diodes. And so there are 4 different methods we will look at. And then at the end, we'll compare the results that we obtain from these 4 methods. And all right, diode circuit analysis. So here is a simple circuit. We have one source connected to a diode via a resistor R. Values are given. Source is 10 volts. Resistor is 10 kilo ohms. We are asked to find the diode voltage VD and diode current ID. Okay, diode current VD and diode current ID. So circuit analysis is, of course, defined as the analysis that we perform to determine unknown voltages and currents in our circuit. So for a diode circuit, you would simply use a appropriate model, convert it into regular circuit analysis circuit, and then just analyze using our standard methods. So first up is the load line analysis. Okay, load line analysis is a graphical technique, and we can apply this to several different. Well, actually, we can apply this to a large number of circuits. Okay, so load line analysis is graphical. Then we have the mathematical model, where we simply take our equations, plug in values, and solve them. Then there's the ideal diode model. It is by far the simplest of all techniques. This is my go-to technique when I first look at any kind of circuit, any kind of diode circuit. The ideal diode model is my go-to model. Excuse me. And then we have the constant voltage drop model, which is an extension of the ideal diode model. Okay. So let's take a look at load line analysis first. To generate an equation for the circuit, you're simply going to apply KVL around the loop, and we obtain this equation right here. Voltage source V is supplying 10 volts. So that some combined voltage is being dropped across the resistor and the diode, right? V is equal to VR plus VD. So if you have a larger diode circuit, what we would do is we would find the Thevenin equivalent circuit as seen by the diode and reduce the rest of the linear circuit to one single voltage source and one single resistor, right? So if you have a large linear circuit, you would apply Thevenin theorem and reduce the linear network, or reduce the linear circuit. So this graphical technique is based on load line analysis, right? So let's explain what load line is first. How many of you are familiar with the term load line? You've heard of it before? Okay. So load line is basically a technique where you're trying to isolate the nonlinear element and the constraints and basically plot the characteristic of the external circuit apart from that nonlinear device. So in this case, a nonlinear device is the diode. Okay. And the external circuit in this case would be the power supply and any resistors that are present in the circuit. So any sources or any resistors that are present in the circuit. Now, our diode characteristics look like this, right? So the characteristics look like this. Where would the diode voltage be? It could be anywhere along this characteristic, right? Yes. Which one? So it's a plot of the current as a function of the voltage, right? So if we know the current, we can find the voltage. If we know the voltage, we can find the current. In this case, both of them are unknown to us. We don't know what the diode voltage is. We don't know what the diode current is. So if we have two unknown variables, we need at least two equations to solve them, right? If you have two unknown variables, we need two equations to solve them. If you want to solve them graphically, we need two plots. We have one, we need a second one, right? So the second one comes from the external circuit. And the external circuit places constraints on the operation of the diode. So because the diode voltage and current can lie anywhere along these characteristics, the point would be determined by the constraints that are placed on the diode by that external circuit. Okay, and if we plot the voltage and current for that external circuit, we obtain what is known as a load line. Again, we have a nonlinear device, diode, and we have a circuit that is comprised of linear elements. So it's a linear circuit. So diode is nonlinear, but apart from the diode, everything else in the circuit is linear, meaning the external circuit can be described by a standard linear line. Voltage increases, current increases. Voltage decreases, current decreases. So a linear line is what will describe the external circuit. In this case, the resistor and the voltage source. Does that make sense? And so we'll plot the load line. That load line will intersect this diode characteristic, and we would obtain this right there. And you see that the intersection point is labeled as Q point. Okay, so the intersection, let me write first, this line describes the external circuit. Okay, and the external circuit places a constraint on the operation of the diode. Okay, external circuit places constraints on the operation of the diode. So now, the intersection point is the solution, right? Two unknown variables, VD and ID. We need two equations, but in this graphical method, we need two plots. One is the diode characteristic plot. The other one is the line describing the external circuit. The intersection point of these two plots give us the solution for the diode voltage and current. Yes. Yes, I am going to. I haven't actually explained it yet. So, all right. So any other questions so far? This graphical technique is very useful. It's not only used for diodes, it's also used for transistors, transistor amplifiers, for all sorts of devices. Yes. So the load line, so the question being asked, what is the load line supposed to be? Load line is basically the line that describes the external circuit. So this is referred to as the load line. And then we'll look at how we'll draw the load line. Yes. Yes, the entire external circuit. Yeah, so the question being asked, what is the load line? The load line is the plot that describes the external circuit. In this case, it describes the voltage source and the resistor. Load line, though, will also take into account diode voltage and diode current because it's part of the circuit itself. Right? It's part of the circuit itself. So the intersection point is a solution. It is labeled as Q point. The Q stands for quiescent. Quiescent. Okay, quiescent point. And you'll refer to this Q point a lot going forward in your studies as an electrical engineer. Okay, quiescent, the word itself simply means lying in a dormant state. Okay, but technically, it simply means, in our case, it means it's lying in wait for some input. Okay, it's lying in wait for some input. So Q point is also known as the operating point. The word quiescent, that's what describes the acronym Q. This is basically the point at which the device is going to operate. So quiescent point, also known as the operating point. And it signifies the external constraint that is placed on our diode by that circuit. Okay. Quiescent, again, simply means it's lying in a dormant state. For our diodes and our transistors and MOSFETs and FETs, it refers to DC biasing of the circuit. We apply some sort of DC input to our circuits, DC voltages and currents. So our devices are now set to operate at a certain portion, a certain point. And then we apply AC signals on top of our DC biasing voltages. Okay. So again, Q point is known as a quiescent point, is also known as the operating point. The circuit is lying in a dormant state. In this case, it's dormant in the sense that the operating point is fixed by the applied DC voltages. Okay. And hence it is known as DC bias. It's also constraint placed on the diode. And we'll refer to DC bias when we get to BJTs, transistors, MOSFETs, FETs. You would apply a DC voltage, DC current to our devices. Now we fix the operating point, and then we apply AC signal on top of it. And we'll put it all together when we do a CE amplifier. That's in lab 8, last lab of 346, last lab or last experiment of the lab class. Okay, pause and let me know if you have any questions.
Hello.
Good. Okay. All right, so let's plot our line. From KVL, we had the source voltage is equal to VR plus VD. we can describe VR as ID times R from Ohm's law. And this is the equation we need to plot. Okay. In this case, the equation is linear because VD and ID are fixed at one point. Okay. Once it intersects, it's going to fix VD and ID at one point. We just don't know what that point is yet. Okay. So if we have a line, we are plotting that line. If we extend it, doesn't matter where it is, at some point, if it's of infinite length, at some point, it must intersect the X and the Y axis, right? That line would intersect the X and Y axes, depending on the slope, unless it's like flat. Yes. So we would take our graph. We have ID as a function of VD. You would plug in both values at 0 and determine the other one. So we'll first plot, not plot, but we plug in VD as equal to 0. It gives us ID as V over R. And then we'll plug in ID is equal to 0. That would give us VD is equal to V. Thus, we have two endpoints of, or at least the two intersection points of the line that refers to the X-axis and the Y-axis. Here, this would become 10 over, what is our resistor? 10K. So 1 milliamp. And this would become 10 volts. And those are the endpoints. Yes. If VD is equal to 0, then it's actually a short circuit. But in this case, we are not referring to open circuit or short circuit. You're simply solving the mathematical equation. So if we plot those points, 10 volts and 1 milliamp, which is right here, we have that line, the intersection point of the line, and the diode characteristic that is given to us gives us the solution for the diode voltage and diode current. The Q point from the intersection point VD comes out to be approximately 6 volts. And ID comes out to be, oh, sorry, not 0.6. And ID turns out to be approximately 0.95 to 0.94. So let's and this is the downside of a graphical analysis. To get very accurate values, you need like a very zoomed in graph or zoomed in plots. Otherwise, the solution would just be approximate. Okay, so the intersection point of these two plots is where we obtain these values. VD is 0.6 and ID is approximately 0.94 to 0.95 milliamps. As a student, if I ask you to solve something graphically, I might accept 0.94, 0.95, 0.955 perhaps, depending on how zoomed in our plot is. Okay. But if it's like 0.96, 0.97 or above, then it'd be marked incorrect. Yes. To find the intersection points of the line, to be able to plot the line. Yes. The question being asked is, why are we plugging in VD and ID is equal to 0? The reason is we have two unknowns, VD and ID. But if we are considering this as a straight line, then we assume that the line would intersect the axes at some point. The intersection point would mean the value of x is equal to 0 at some point, and the value of y for the other coordinate is 0 at some other point. Meaning at some point, where there's a line of infinite length, at some point, that line is going to intersect x and y axis. If it intersects the x-axis, y is equal to 0, meaning current is equal to 0. Intersects the y-axis, x is equal to 0. So we plot VD and ID is equal to 0, and we obtain the other quantity. All right, other questions? The steps make sense. Again, load line is not just for this diode. It can be used for Zener diodes, BJTs, FETs, MOSFETs, all devices. Okay, so it's an important technique. All right, one final point before you go to the next method. Since this voltage and this current are at the Q point, we often try to note this with a subscript of Q. So VD at the operating point would be VDQ, and ID at the operating point would be IDQ. So the Q simply notes it's the voltage and current at the operating point. Okay, so VDQ and IDQ. Okay. Next method, mathematical model. Determine the Q point, same diode, same circuit. But now we are given IS is 10⁻⁻13 amps, N is 1, and thermal voltage is given as 0.025 volts. So now, this is where we'll use the diode equation. So the diode equation is ID is IS times e raised to VD over NVT minus 1 . Okay. ID can be written as that same circuit. Actually, simple Ohm's law. It's a series circuit. Our voltage, again, I'll draw the circuit here so we don't have to go back. It's a series circuit. So the diode current is also the supply voltage current. It's also the resistor current. So we can find the diode current by simply applying Ohm's law to that resistor. And that's what we did here. We have 10 volts here. And we have diode voltage. So the two ends of the resistor are at 10 volts, and VD current's going from left to right. So it's 10 minus VD over 10,000. One equation, two unknown variables. Now we can find VD by manipulating the other equation above. So we can write VD is VT times ln or log of ID over IS. But we are still faced with the same dilemma. We have two unknowns, VD and ID. We can do one thing, and that is plug this into this equation ID, and we can obtain just one unknown variable. And so I can write VD is T times ln log of 10 minus VD over 10,000. So mathematically, yes. Plus 1. Where in this one? Let's see. ID over IS plus 1. Is that what you're referring to? Good noticing that. So what I'm going to do here is I'm going to say, since n is equal to 1, that's out, obviously. And I'm going to assume ID over IS plus 1 is approximately equal to ID over IS. Because IS is so small, typically nanoamps, compared to a diode current, which might be in milliamps, that's quantity is going to be far larger than 1. So the plus 1, if I wanted a more accurate value, I would keep it. But to simplify it, I'm just going to get rid of it, and I'm going to say ID over IS plus 1 is approximately equal to ID over IS, since IS is very, very small. Does that answer your question? Okay. So what I've done here is I'm trying to solve this mathematically, took the diode equation. The diode equation, I can rearrange to obtain an equation for the diode voltage, right? We simply take IS on the other side, take log on both sides or natural log on both sides, and we obtain an expression for diode voltage. I want to keep the terms as low as possible, the number of terms, meaning I have one voltage, thermal voltage in there, and then I have VD. And then I obtained a equation for the diode current from the circuit, right? Applied Ohm's law to the resistor, obtained an equation for ID. The entire purpose of this exercise is that I want to remove as many variables as possible, right? So I plugged ID equation into the diode voltage equation, and I obtained this right here. This equation, much like the equation that I had on the quiz, cannot be solved directly. You need some software or need to perform iterative analysis. And so we have our second method where we use an iterative analysis to arrive at a value for diode voltage. Yes. IS where? No. So since IS is very, very large, I'm going to ignore, I'm sorry, ID is large compared to IS. I'm going to ignore IS. Yeah. So it's going to be much larger than compared to IS. I'm just getting rid of it in my equation. We can keep it. We can keep it. And it's not going to make too much of a difference. And you will see that on the next slide. So I'll have equations that solve, not equations, calculations that solve this equation. And I was going to assign students where you would not ignore the assumptions and solve it with all the values in there. So let's get to the next slide first. So what we would do is in iterative analysis, we pick a starting point. We choose a starting point. I'm almost out of time. In this case, I'm going to choose VD is equal to 0. Even though I know typically VD would be close to 0.6 volts, I'm going to start with 0 volts. Then you check your answer. Does answer match up assumption? If not, you plug in the answer as your starting point. We are out of time, so if you have to leave, you can leave. I'm going to continue recording with the explanation. Okay, so what I'm writing here is, first we choose a starting point. We calculate the equation, look at the answer. If the answer does not match our assumption, we repeat steps 1 and 2. This time, we'll plug the answer back into the equation at the top. Then we solve it again. We keep solving it until our answer matches our assumption. And that's why it's known as an iterative analysis. What happened? There we go. So this is created simply in Excel. This is my starting assumption, VD, right here. Okay. Starting point. And these are my answers for VD. I could choose VD as 0.6 and begin from there, but I just wanted to show you how quickly you can arrive at an answer, even if you choose 0 as your starting point. So I have that equation, right? In that equation, I plugged in VD is equal to 0. I plugged in VD is equal to 0, and I obtained 0.594 as my answer. I take that answer because it does not match 0, obviously. Oh. 0.94 does not match my answer, so I plug in there. So I skipped a couple of steps. And you plug it in here. Okay. So I went to then 0.65. When I plugged in 0.65, I obtained 0.5923. That still does not match. So I plugged in 0.5923. And I obtained 0.5924. That's still, well, actually it matches, but I wanted to just make an example. So I went like 5, 6, 7 times down the line. And then, right, as you can see, if I start with 0.65, I have a matching answer within 2 tries. Right there. Right down to 5 decimal places. If I was stopping after 3, I would be done in like 2 steps. Okay. So iterative analysis is you choose a starting point, you solve the calculation, see if it matches up with your assumption. Otherwise, you go back and you plug that answer back into that equation and you solve it again. If you use a software, it gets done in seconds. Okay. All right. We'll then stop here, and then we'll pick up here again on Wednesday. Solve the same equation without the assumptions. See how many tries you get. Meaning you write the equation by including IS and by including the +1 in the equation. Okay. It would just be a slightly different equation, but you will still arrive at pretty much the same answer.